Okay, so I guess begin by particularly thanking Jan. It's always a pleasure to come to Singapore. I've been a few times in recent years in relation to the EU complexity effort at NTU and now Paralimas as well. And it's always a great pleasure to be here. I really enjoy this interdisciplinary ethos which seems to be thriving here. I am in a mathematics department, and I'm kind of culturally a theoretical physicist. So my kind of talk is going to be very much on the scientific side, but I didn't really know what was going to be the audience that I was expecting. So I kind of tried to really not get into very technical things, and so my discussion is going to be much more at the level of overview, and I'm not really going to talk about any of my own research, which is perfectly fine. And I want to talk about stochasticity in models of complex dynamics, or models of complex systems in general. And I should begin by kind of saying that we've discussed a lot in the last day about sort of complexity as a concept, and we think of being able to classify systems in some dimension of complexity. On the one hand, you can have systems which are complex and they're not reducible into individual components, and the complementary idea is that there are systems which are simple, where you can. And then there's kind of the world of models, which is mathematical equations or computer simulations. And in the world of models, you can have simple models and you can have complex models. And then you can also have models which are, in some sense, an alternative axis is models which are deterministic and models which involve random variables, so are in some sense stochastic. And these are related concepts, but nevertheless they're kind of different dimensions which one can sort of classify models. And what I want, the main message of my talk is that since we're thinking about how to construct some kind of lens for converting observations of a complex system into some kind of understanding or some more digestible sort of view, the main point of what I want to say today is that I would make the argument that for such a lens to really work well, to be useful for people who are not specialists in simulation or mathematics, this lens must come up with a way of making evident the role of randomness, either intrinsic randomness in the system itself or randomness which is being used in the model in order to kind of somehow simplify the description or capture effects which we don't want to model in detail. So this is the kind of take-home message. I'm trying to convince you of this. Do we have to keep walking up and down?
Yeah.
I do. Okay, fine. So let me begin with a parable. So this is the parable of the blind man examining an elephant. And this parable, I guess, is common in lots of Eastern traditions and is now well known in the West too. I think it has its origins very much in the Asian way of thinking about things. And the idea is you have some reason which I never understood. A bunch of blind men are told to examine the elephant, and they're only allowed to individually look at some part of the elephant. And so the guy that is looking at the tail says, well, this whatever this thing is, it's like a rope. The guy who is feeling the leg thinks, oh, it's kind of like a tree trunk. And the guy who's climbing on the back here concludes that this thing is like a wall. And the moral of the story, this isn't given a lot of different meanings, and I think it's a very kind of rich parable actually in lots of ways. But for purposes of today's discussion, I think that the moral of this story is that if you think of the elephant as a complex system, and us as scientists, we never get the full story. We observe imperfectly, or we observe some of the data, but we never observe everything. And what one can conclude from this story is that scholars observing the same complex system in different ways, you can form different perspectives, and although they're all technically correct individually, they may easily miss the whole story. So I think that's really important to bear in mind. Whenever you're talking about models which are built on data, you've heard yesterday, that, particularly in the context of economics, that you never can get all of the data that you would require to compute some expectation, some kind of fitness function that you want to maximize, even if such a function existed in principle. We always have incomplete information. And this this kind of problem is a perennial threat. So one aspect of complex systems, which is commonly discussed, this idea of kind of complexity between order and disorder. So this is not a mathematical statement, and I don't really think it should be made into one, or at least not in general, but qualitatively, complex systems often appear to be neither completely ordered nor completely disordered. So there's this kind of edge of chaos theme, which has been in this community for quite a while, and instead of saying that the interesting stuff happens when you're somehow in the middle in terms of completely ordered is the domain of equilibrium physics, and we understand very well. Completely disordered is basically just a random process which, although it may look complicated, actually contains no information. And in between you have complexity. That's maybe one way of thinking about complex systems. And if we're going to do complexity science, then when we have such systems which are somewhere in between ordered and disordered, the objectives, what we really want is, basically we want, first of all, an increasing level of difficulty. And first of all, we want understanding. Ideally, from the point of view of policy, we want then to convert this understanding into ability to predict. And then maybe, in some cases, or maybe not, this may then lead to the ability to design or control systems. Let me give an example, and this is, the one place where I will touch a little bit on my own scientific interests. And this idea of being neither completely ordered nor completely disordered. A really good example of this is the coexistence of order and disorder in turbulent flows. So if you look at a picture like this, so this is a snapshot of the vorticity field in a turbulent flow, and what you can see is that certainly visually you can see there are patterns, there are vortices, there are long filaments. If I would play the movie, which I think I may not really do, just in case movie problems last, maybe other people are interested later, I can show, but this is very beautiful dynamics. Most of you have an idea of what turbulence looks like. And if you have some particle which is sitting in there, you see that the individual particles which are swept around, and if you look at a time series, the position of such a particle looks a little bit like this. This is really from numerical simulation. It has some degree of regularity, but also looks in many respects random. And so despite the fact that you have a lot of coherent and sort of structured objects in here, you nevertheless have also a lot of disordered fluctuations, and there tends to be a separation in scale between the two. The ordered structures more large scale, the more random looking dynamics are smaller scale. So this is the kind of stuff I work on, trying to understand that. I think it's a good example of a complex system. It's a critical difference from some of the things we were looking at yesterday is this is not adaptive. So in principle we can write down all of the equations for this. And these equations don't have any intrinsic randomness in them. The sort of effective randomness just comes about through nonlinear interactions between different scales of motion. So it's a good way, this is a good system to kind of think about some of the issues which come up in complexity. Maybe not all of them, as I said, there's no notion of adaptation here. So other examples of this, well, you can pick many. I think you've even heard some of these, where if you look at economic trends, there are some long-term cycles with lots of shorter-term variation. Likewise, neural activity seems to show, if you look at EEGs and scan, there's some patterns, but there's a lot of fluctuations as well. Epidemics are the same. Overall, deterministic, there's a general trend of growth, peak, and then decay, but individual realizations fluctuate a lot. That's why kind of things which are Ross atmosphere I was talking about yesterday are so difficult to really predict quantitatively, traffic flow. All of these things, which we think of as being complex systems, exhibit this property of looking somewhat structured, but not structured enough that you can just really easily predict individual instances. However, I would make the point that pointing at such a broad commonality doesn't necessarily tell us actually what should you do. So I would say, well, one thing that you could do is to use what we in mathematics call stochastic modeling, and to at least come up with a way to make these things quantitative and start thinking about them. And the idea is to use a simple, in quotes, model for the coherent structures, so the underlying deterministic dynamics or trends or whatever are the bits that we think are sometimes structures of the system. And then to model the fluctuating dynamics as random, in some sense, which maybe I'll make a bit more precise later. And then assume that given this randomness, we're only interested in the average behavior. Of course, in practice, this separation is never clean. If it was clean, somehow this would be trivial. What actually happens is that in practice, whatever we identify as being the structures and whatever we identify as being the fluctuations are coupled to each other, and they interact, and they feed back on each other. And so separating them out, this is an example of kind of reductionist way of thinking, but maybe at slightly higher level. So an archetype of this kind of model is one, I guess, again, drawing a little on my own interests, is climate, where essentially large scales in the atmosphere are modeled very accurately by the equations of fluid dynamics. But small-scale phenomena, basically the weather, small-scale for climate means things on the scale of kilometers. So it's maybe not small-scale for a human, but it's small-scale for the planet. And so whatever these processes of evaporation, convection, and here, one of the interesting things about these kind of models is, if you live in Singapore, we've already seen some of these very spectacular thunderstorms. And these are convective events which are happening on the scale of kilometers, and they're actually entirely absent from the models which we use to try to predict what the climate's going to be doing. So the point is that in these examples, what we want to do is treat such small-scale events as somehow as fluctuations and average over them in order to get the behavior of larger scales in an average sense. So I don't think I really need to go into a huge amount of detail. I'm not going to give a technical talk, but in the mathematical sciences, and when I say mathematical sciences, I mean mathematics, but also statistics and some parts of computer science. These academic areas give us the tools to handle random phenomena quantitatively. So we have a theory of random variables. And when I talk about a random variable, I just mean a variable whose values represent some outcomes. The example, of course, that one gives rolling a dice. It can be discrete or continuous. The main point I just want to make is that you can characterize a random variable mathematically by essentially its probability mass function in the case of discrete random variables, or probability distribution function or density function if it's continuous. And what this function just does is sort of tells you the relative likelihood of different outcomes. So everybody has seen the normal distribution, which roughly it's saying that this random variable, most likely outcomes are sort of here around the mean, but you have diminishing from further away you get from the mean, the less likely that outcome is. And the other sort of important part of this is what are called random processes. Since we're going to talk about sort of using observational data to try to model something complex system, even a non-complex one, it's usually helpful to be able to model time series, see a lot of them. So natural model of a time series is what we call a random process. So it's just a sequence of random variables which are ordered in time. And here are some examples. Two simplest ones. What physicists call white noise. It's basically just a process where at each moment in time you independently get a normal random variable. So it's a very rough and hairy looking thing like this. It just fluctuates independently at each point in time. And more useful in most cases is a random walk, where basically there's little memories of the value. This thing, what a random walk does, basically it fluctuates up and down more smoothly than this white noise, and the value of that time t plus delta t is the value of previous time, so they're not independent anymore, plus some increment. It included a deterministic part, it's called the drift. This random walk is on average going in one direction or the other, plus some fluctuation part, so stepping for down each step randomly. All right. So these are the kind of things, and it's enormous theory in mathematics about variable stochastic processes, which I'm not going to go into. So this is the first, maybe, time to start thinking a little bit. Now, this has been by way of introduction. If we want to use some of these tools which mathematical scientists have given us to model some particular system, before we plunge into writing equations and doing simulations and so on, it's worth just stepping back and thinking a little bit what it is that we're actually doing by saying that we're going to model some part of the system, say the small-scale fluctuations, using a random process. Because there are different flavors of randomness in the world in general. Some systems, quantum systems, really are intrinsically, as best we can tell from physics, they really are truly random in their nature. Other systems are not random, but look random for all intents and purposes, so most of you know the idea of deterministic chaos. You have a system which, although it follows a deterministic rule, if you actually look at the output of this rule, it looks, for all intents and purposes, you can't distinguish statistically from the random process. At the level of modeling, sometimes people will use, for example, in the climate model, you'll use randomness essentially as a tool. It's not necessarily intrinsic to the system, but you want to use a random function to model unobserved degrees of freedom. If you're only interested in it, if you can only afford to simulate the large scales, you might treat things which are happening on smaller scales as being random. It doesn't mean you necessarily believe they truly are intrinsically, but you just don't have the knowledge or you don't have the computer power to resolve them. And so this is different from the first two. And then people also use randomness or random variables as a way of quantifying the fact that measurements of the system are themselves not completely accurate. And this is more or less always true. Anything you measure in the real world has some error associated with it. And if you're going to plug these numbers into some kind of model, particularly a nonlinear model where you have feedbacks, these errors can become amplified. And so uncertainty you need to track how that uncertainty may propagate through your model. And so assigning a probability distribution to a measurement is often a very important thing to do if you want to keep track of uncertainty in subsequent calculations. And another thing that people would sometimes use, and I put some question marks after this, is model error. So sometimes people will use a random variable to model the fact that the equations of the model you're going to use might be wrong. Now this is questionable in some ways. And we heard already yesterday about, in the economic context, the distinction between risk and uncertainty. So risk is essentially the possibility that it's variation which is quantifiable. You know that there are different outcomes that can happen, and you can ascribe probabilities to them. Whereas uncertainty is things that can happen that you haven't included in the model. And these are kind of different, and I'm actually not so sure. You can use an appropriate probability distribution to model risk, but it's, I think, very dodgy to claim that you can really treat uncertainty in the same way. So the point of all of this is that essentially the meaning of randomness that you might use in a modeling context is a little bit dependent on what you're doing. And so some intuition and understanding is really required. It's not a black box tool, even though people sometimes use it this way. Some understanding really is, some thinking is required before you plunge into this. But what one finds when one works with these kind of things is that actually one's intuition when dealing with random phenomena is kind of often wrong. So I want to just maybe talk a little bit about this and just give some simple examples, and I apologize if many of you know these things already, but they're worth just thinking a bit about this. So firstly, we as humans are actually not that good at recognizing randomness when we see it. So here's visually, our visual system finds it difficult to distinguish whether a pattern is random or not. So what I've done here is I've just plotted one of these pictures is a sample of uniformly distributed random numbers on random points on a square, and two of them are the output of so-called low discrepancy sequences, which are essentially deterministic rules which try to fill a space by essentially putting points in the gaps, try to make it a kind of a uniform distribution as possible. And at least to me, it's difficult to tell which one was generated by a purely random process and which one are actually deterministic things. I don't know if anyone wants to try and guess. Here there's 100 points. No one wants to hazard a guess. But I'll make it a bit easier if I show you 1,000 points. I think you can start to see, well, at least the one on the right is clearly not random. The uniformly random one is this one. So the point of this little exercise is I say it's kind of difficult to distinguish between 1 and 2. And so you really need to do, you need something a bit more than your visual intuition to solve this problem. And another example which I always like is conditional probabilities are essentially probabilities which are dependent on, so if you have one event, what's the probability of an event given that you have some additional information about some event which may be correlated with it. The study of such problems is called conditional probabilities. And an example which illustrates the fact that we don't really think well about conditional probabilities is the so-called Monty Hall problem. This is a kind of simple example, but conditional probabilities are important because they're the way that we use the tool we use for encoding relationships. So the idea of Monty Hall problem, and I guess how many people know this already? Probably a handful. Well, enough people don't for me to spend a minute just to say. So basically there's 3 doors, and I know that behind one of these doors is a car, so it comes from a game show originally. So you guys got to try to win a new car. So behind one of these doors is a car. Behind the other 2 is a goat, and I don't know why it's goat, but somehow in all of the examples of this, maybe in the original show it was a goat. So the rules of the game is you pick a door, and then you tell me which door you picked. Now remember, I know where the car is, but you don't. So you pick one of those 3 doors, and then you state your choice, and then once you've stated your choice, let's say you pick the first one, I then show you of one of these other 2 doors which one has a goat. And so let's say you pick the first one, I open the third one, the goat is there, and then I ask you, well, do you want to swap your original choice for the second door, given that you know that there was a goat in the third door? And so the task that you need to answer is, firstly, should you swap? And if so, what's the probability of winning the car if you swap? So most people, I think, would say, well, the probability is 50-50, so it doesn't matter whether you swap or not. Now this is wrong. You should always swap. And if you swap, the probability of winning the car is actually 2/3. So a lot of, most people get this wrong, including famous mathematicians, by the way. Erdős is the one.
Yeah, not only did he get it wrong, but he didn't believe the explanation either.
Yeah, he really. This is an interesting story in its own right. So I have to kind of think about this, and we can discuss. Hopefully, there are some of you who think that I'm essentially misleading you by saying that the probability is 2/3. But this question, the issue is, well, nothing changed, right? How did the information propagate? But it's to do with conditional probabilities, and I won't tell you the explanation. There is a simple explanation. We can discuss over coffee. And here's another example where intuition can go wrong. So naively, you might expect that things like phone numbers, credit card numbers, financial transactions, etc. If you look at say if you think of the digits of these things, you might expect them, they didn't come from any particular generative process that we can know of. So you might expect that the digits of these numbers would be uniformly distributed on 1 to 9. And actually, they're typically not. And the fact that they're not is known as Benford's law. And it's not it's law in books. I mean, there's no derivation of this law. It's an empirical observation. What this guy found is that the probability, so basically, if you look at the leading digit of things like phone numbers or credit card numbers, financial transactions, etc., that they start with 1 far more often than with other numbers. And actually, if you look at the probability mass function of the leading digit, 1s are overwhelmingly more probable than 2s, 3s more than, and very few of them actually end up starting with 9s. But this phenomenon, you might think, well, why is this? And I don't think there's really a convincing explanation. And it's not to do with the fact that we work in base 10. The 1 doesn't come from having 10, because this phenomenon is independent of the base. And you can think about this, and maybe you don't believe it, but it's true. But the thing that I found difficult to believe is that it's also approximately true when you look at the leading digit of physical constants in the universe. So this is not something that comes about just from something to do with the way that we make up phone numbers. It really has some, a lot more of the physical constants, speed of light, charge of the electron, Boltzmann's constant, etc. These are natural things. A lot of them, more of them start with 1, overwhelmingly more than with 2, 3, 4. So the conclusion of this is just an intuition of random numbers can be a bit risky, so we really do need mathematics and we need statistics to do these things properly. So let me now just move a little bit and kind of start picking apart some of the kind of things we might want to really, statements we might want to make in the context of stochastic models. And in the end, I guess people who want to make decisions want to be able to understand from looking through their lens or whatever, or from discussing with experts, they want to know that on average X causes Y, basically. So you observe some variable X, and we want to be able to know that on average we see X and we see Y, or not. So this is the kind of statement which we ultimately would like to make by observing real complex systems, in which I would argue any kind of useful complexity lens should make somehow evident to people, without having to really learn a lot of the machinery of statistics and probability theory. So this is basically to start with descriptive statistics. So it often relies very heavily on linear regression, where we posit a relationship between two quantities, y and x, and so we make some relationship, assume some relationship like this exists, y being, doesn't necessarily, it could be more complicated than this, but one important point is that it should be linear in the parameters. Parameters are, these are the unknowns, alpha and beta. And maybe, and anyone who does this a little bit will know this, but it's not always well appreciated. And generally, that linear regression is not quite as bad. You can say, oh, descriptive statistics, everything is linear. Well, not everything is linear. I mean, there's no reason why. What's important is that this relationship is linear in the parameters. You can have nonlinear relationships in the data. That's fine. I could put x squared, x cubed here. So it's not true that linear, what we call linear regression, can't model nonlinear relationships. It can. And the important point here is that whatever relationship you're positing should be linear in the unknown parameters. So one shouldn't be too harsh on good old linear regression. The point is, however, you view this, once you know these regression coefficients, then essentially knowledge of x, imagine that knowledge of x then gives you some knowledge of y. Maybe imperfect knowledge, some scatter. The two should be related in some way. So I want to spend the rest of my time to kind of pick apart just statements like this, on average, x causes y, and try to bring out some of the implications of the assumptions which underlie, because a lot of people who are not scientists, who are not statisticians, when they read a statement like this, they tend to just sort of say, well, let's get rid of the first two words, and we just simplify. So it means X causes Y. Therefore, policy, if we want to increase X, we increase Y. So first of all, an average, what do you actually mean? So firstly, the average of a random variable is defined mathematically as just actually the weighted, you sum over the possible outcomes weighted by their probabilities, and then you get a number which is called the average. And in practice, if you don't know the PDF, which you usually don't, then we have what everybody learns in high school, the sample mean. And that's just a mathematical statement. Now, if we transpose it into English, average does not mean typical, expected, or representative. And this, again, very clear to people who know this, and often unclear to people who don't. That the nomenclature is very unhelpful. Mathematicians call the average the expected value. We use average colloquially to mean sort of typical, representative. Actually, mathematically, it doesn't. It depends on what is the probability distribution and what is the process which we are averaging. And here's a simple example of where the average may be either typical or atypical of a particular realization. Often what we care about is not, what we care about is the realization we see. So often knowing the average may not be useful. So the red curve is a normal distribution where indeed the average is, now both of these distributions have average 1. It is fixed it up this way. The normal distribution is peaked at 1, and typical samples from this distribution are going to be mostly clustered around 1. So for this particular case, the normal distribution, it's actually all fine. We can think of the average as being representative, and it's a good indicator. Now this other distribution, the green one, is one which comes up in, again, I've taken from theory of turbulence. It's basically the product of two correlated random variables. So that distribution is not normal, and it looks like this. And basically, the most likely value that you see is 0 for this PDF, despite the fact that the average is 1. Now, the reason why the average is 1 is because large positive values are much more likely than large negative values. So the average is somehow a result of cancellation of large fluctuations. That you have probability of a large fluctuation in one direction is much bigger than the probability of large fluctuation in the other direction. And when you plug this kind of stuff into a formula like this, kind of dominated by the small number of really big ones, which gives you an average of 1, but actually 1, at the level of individual realizations, the number 1 is not really telling you much at all. So that's very important to bear in mind. You don't necessarily think that an average is typical. It depends on what you're doing. So some knowledge is required again. And here's another very important concept, which here maybe I'm getting into things that maybe fewer people know. Because what do we mean by an average anyway? So there are many ways that one can compute an average. Essentially, mathematically, it means specifying a different sample space or a different probability distribution. But two very commonly used ones in sciences are time average, where basically we take a time series and we compute the average over the points. And then the ensemble average, different concept, which theoreticians like very much. And the idea of an ensemble average is that we average over independent realizations of the process. So the ensemble average you can think of as an average over parallel universes. But it's not something that we typically don't do it in the real world. Maybe in the lab you can do many experiments and you're repeating something many times and compute an ensemble average. But a lot of averages which appear in literature tend to be time averages, because these are easy to compute from data. A lot of averages which are computed in theoretical literature tend to be ensemble averages. And the key point is that although there are a class of systems for which these are equivalent, for the fact that in general these are not equivalent. So if these two things are the same, then the process is called ergodic. And ergodic processes are a kind of special subcase of general stochastic processes. And most random processes are not ergodic. And I just picked one example out of a couple to show you. Geometric Brownian motion is a stochastic process which is used very commonly to model movement of stock prices, for example. Finance people like it. It's not ergodic. Basically what it is, it's a random walk exponentiated. So you can, if you like formulae, you can write down the rule for stepping it forward this way. So it's basically a random walk for the log of x. It has a drift mu and then some variance sigma. Eventually fluctuations are introduced here through this random term. And if you would calculate the ensemble average of geometric random motion, then what you get is basically an exponential. So ensemble average, again, you realize this process many times, and then you just average the result. And what you get is a function of time which grows exponentially. So that's on this picture, which I've taken from a friend of mine, Ole Peters, Santa Fe Institute guy, many of you probably know. So he's done this. And the ensemble average basically grows exponentially. So you might think, well, geometric random motion, if I know what the drift rate is, I could expect that if I take the average to be representative, then I can work out how much my portfolio is going to grow over a certain time interval. True, if you have a sense, if this is going to be some sense of using this to model a diversified portfolio where you have lots of independent stocks, all of which are going to be executing individual, independent geometric random motions. If, however, I'm kind of a silly investor and I just pick one stock and I'm just going to invest that, then I don't care about the ensemble average. What I care about is the time average of that particular realization. This is different for this system because it's not ergodic. And actually what you can show, and what this picture tries to show, so what Ole and Phil Klein have done here is plotted the blue lines are essentially the quantiles of the individual realizations. So somehow this is the 95th quantile, the top blue line. I forget about all the other ones. And what this shows that individual realizations are below this line 95% of the time. And this is a logarithmic scale, so the fact that there's a big difference here between the ensemble average and the sort of quantiles of individual realizations this is not a little difference, it's a huge difference. And actually what you can show is that the time average over a sufficiently long time, the time average of individual realization for this process is 0. So forget about your expected exponential return after 100 years. Typically, most realizations are going to be worth nothing. So it's important to distinguish between ensemble average and time average. And much of the literature actually doesn't. I mean, this is a little bit strange. So here's another example of non-ergodic behavior. So this is polyazarn, which again is a model which I expect many of you will have come across. And it illustrates, again, some slightly nice features in a simple way. It's not a model of anything, so I'm not really talking about complexity anymore, but I want to just make you think about some concepts. So the rules again here, you have an urn, a joke, and that initially contains one green ball and one red ball. And the rules are, well, you put your hand in, you draw a ball at random, you look at what color it is, and if it's red, you put back in 2 red balls, if it's green, you put back in 2 green balls. And you just repeat this step until you reach an agreed number of balls in the urn, typically some large number. And the question that one is asked to answer is, well, what proportion of, say, green balls do you expect to find in the urn after you repeat this process for a long time? And I often give this as an example to teach a course on data analysis and stochastic processes at Warwick. And we often do this in the class and get the students have some joke with red and green balls, and we really do it. And ask the students to kind of guess what will be the outcome. And usually, at the beginning they're kind of wrong. A lot of people say, well, there should be about 50-50. And then as the urn goes around the room, people at the back tend to have a much better guess. Say, oh, it's not going to be 50-50. And they start to somehow think about it. And so if you do some numerical experiments on this, you can understand what's going on. So let's just do one experiment first. So let me call Fn is the number of green balls after n steps as a proportion. So this is going to be the fraction of greens. And so here's just one numerical simulation of this process, and you see it sort of fluctuates quite a lot. But as time goes on, the fluctuations in this proportion start to die out. And although this is an entirely random process, it becomes quite deterministic as you step on in time. And here, in this realization, this proportion becomes about a third as n gets large, and it kind of stays there. Now, the interesting thing, firstly, most people won't guess a third, unless you've seen this before. But even if you did guess a third, you'd be wrong, because actually what you find if you repeat this process is that each time you repeat the experiment, there's lots of them, then it always becomes deterministic, in the sense that fluctuations tend to die out, and this process tends to really go to some particular fixed value for large time, but that value turns out to be different each time. And the limiting, what you can show by solving this problem in detail mathematically is that the limiting value that you get turns out to be a uniform random variable on the interval from 0 to 1. So most people don't guess this. And the reason for it is kind of, well, basically the early outcomes are more important. So it's actually this is a great model for some of these problems in biology, where this kind of path dependence. And I guess it is useful. So it's kind of a cautionary tale for complex systems research, I think, in general. So we just kind of make a few points about this thing. Firstly, the dynamics are entirely random by definition, but the aggregate behavior becomes predictable over time. So that's one thing to just bear in mind, that you can really have predictability emerging from just purely random rules. There's no fitness, utility, selection, equilibrium, optimality. There's none of these things here. An excess of one species over the other, one color over the other, emerges by pure chance, but persists indefinitely. And I think this one's important as well. When we were talking yesterday about proximate explanations for, say, urbanization and things like this. So with this model, it's retrospectively understandable in the sense that once you've seen a realization, you may say, oh well, the reason why you mostly have red balls is because the first ball that came out was red, and so was the second one, and then after that, it's more or less clear why most of them should be red. But this is not really an explanation, well, it is, and it's true, but it's not an explanation in the sense that if you would repeat the process, this explanation actually doesn't tell you anything. So you can somehow understand retrospectively, but not, it doesn't allow you to predict something new. So I'm kind of around this. So this is not my, I'm telling you stuff that Brian Arthur has told us a long time ago, but these things deserve to be told many times. It's again an example of a non-ergodic system. So I'm kind of running out of time. So let me just skip very quickly. I'm not going to go into details on these slides, but just, I had a list of things which I thought that people should really pay attention to, just on a non-technical level, for this, on average, A causes B type statement. So one thing is, you have to actually be careful what you mean about causation in these kind of statistical arguments. And a simple example here, if we have, say, something, some variable x, some quantity x and y, and we have some unobserved quantity which correlates to both of them, we could do a regression of x and y and find that they're strongly correlated because they're both basically depending on something we're not seeing. This is extremely common in complex. People talk about graphical models, there's a whole field of probability theory devoted to this. The point is that although you find strong correlation in this example because of this unobserved variable, there's actually no causal relationship. You need to watch out for this. And there are ways of kind of trying to get at it. Granger causality is a simple one. How much time, Nick? You said 5? Am I running? I'm down to 3. All right, let me say something a little bit. In 3 minutes, I can't talk about everything to do with modeling, but what I've talked about until now has been just descriptive statistics, basically, and this is what you might think of call sticky wickets that come out of averages behaving subtly. But if you want to go beyond that, you basically need to do some modeling in a bit more detail. And, what I would call a model is essentially an assertion about how the observed data was generated. So that's what a model is really. And it's much more powerful than just a correlation, because it allows you to, you can explore things within the model. So the model will typically have some parameters, and you have a formula for say, the distribution of some data. So the example I picked is, I suppose you have random variables between 0 and 1, and you want to model their what's generating them. Well, a beta distribution is a popular choice because there's two parameters, alpha and beta, and by varying these parameters, you get a huge amount of huge flexibility in what shape of probability distribution you can measure, you can produce. So if you can use the data to find the right parameter values, you can tend to get a good model of the data, and then you can ask questions about it, which what would happen if I vary some parameters. So there are ways to do this. Statisticians have lots of nice tricks for model fitting. But one other conceptual thing that I just want to talk about, and then I'll finish, is this problem of overfitting. So it's again a slightly counterintuitive concept. So let's suppose we want to fit. So we have some data, and it's a very, very simple example. We have some observation, some true way of generating the data is a sine x curve. So we measure some values of sine t by x, contaminated by some noise. So we get this scatter of points, and we want to make a model of this to try to learn what's the process that generated the data. So, well, okay, one particular model would be to try to describe this data using a polynomial of degree m minus 1. So this model has m parameters. So I can make it arbitrarily high order here and try to fit this to the data. It's an example of it's a nonlinear model. Right? So you can do linear regression on this, but you have a nonlinear relationship between the observations and the data. So what you can do then is, let's suppose so the question is, how many parameters should I pick? And so including more parameters makes the model more flexible. In a sense, it makes it more real, more realistic, should I say. It can better fit the observations that you have. So what I want to show you is just, let's suppose we try to use the red observations just to fit this model for increasing values of m. And so as you increase n, you see that it does better and better at fitting the red points. And at some point, there's enough parameters that it can really go through all of them. And so you have a very realistic model of the data. But this actually makes your predictions worse. So the green points, if you want to try to use this model to predict what are the values at the green points, you find that at some point, so it starts off pretty bad. So, it's not a good predictor for low numbers of parameters. It's not flexible enough. But at some point, if the number of parameters gets big, it's also very bad, because it kind of tuned itself to fluctuations in the observations. So this is called overfitting. And it's a perennial problem in statistics, and statisticians know a lot about how to get around it. But it has this kind of counterintuitive aspect that essentially by making a model superficially more realistic by including more details and more parameters, you can actually make its ability to make prediction worse. And that's something that I think not a lot of people who are not trained in statistics appreciate well. And as scientists, we have to really struggle to put this across. Let me stop at this and just make a few conclusions. So I'm kind of arguing that accounting for uncertainty properly is essential to any attempt to understand or visualize complex systems, but our intuition can sometimes be misleading. And I've just gone through a few examples of how it may be. So average may not be typical. The ensemble average and time averages are commonly used, but are generally different, and you should account for that in making decisions. Conditional probabilities in general are just confusing. Correlation is not equivalent to causation, which we all kind of know this as a meme, but mustn't forget it. And then finally, this point which I just touched on briefly, that making a model more realistic can actually make it worse because of this overfitting problem. And so let me just finish by saying, getting back to the blind man, that we always, when assessing these various issues, we should always remember that we may be like the blind man, and you're only seeing some part of the story. Thank you for your attention.
Thank you, Alf. Questions, please. Can I have the microphone?
Throw it out sharp, thanks.
There should be a microphone.
Can I sort of hit on that last one?
Yeah.
We all know the problem of overfitting, and it seems to be endemic in absolutely everything.
Mm-hmm.
But if one asks the question epistemologically, as opposed to, as it were, the empirical experience with the application of statistical overfitting, why is it? Is the problem...
What causes overfitting?
Well, what I'm getting at, you know, the way you phrased it there, making them more realistic can make them, just take the last one and then we'll come back to it. What you've said is making it more realistic, in quotes, can make them less predictive. Now, that raises sort of some interesting questions. Does it mean that we're incapable of creating models that adequately simulate the reality that we're seeking to model? Or does it mean that there is an inherent element of stochasticity in it that is then exacerbated, as it were, by the process of overfitting?
So I would say that overfitting, this is intrinsically tied to the stochasticity.
Clear.
Right? The fact that our observations of the system are not perfect, and that there's noise present. And so if you would, in a sort of a thought experiment, you could imagine that the system really, there isn't any noise, any randomness, and you really have a completely deterministic rule for how the system is evolving. And in that case, in principle, there shouldn't be a problem of overfitting if you can learn the right model. In practice, and even in the deterministic case, what you find is that the randomness that comes from numerical computation, the fact that we don't do numerical computation exactly, is enough to synthesize this problem for us, even in situations where things are in principle deterministic. So I think one can get into a kind of a philosophical debate about really what's meant by randomness or determinism, and that's interesting discussion in its own right. But this problem, as described here, will be there in practice in both cases.
Can I just follow on one very quickly, because it goes to Jan's point in response to us. What I think we all sort of try to grapple with in this particular space is what lessons can we learn out of effective retrospective learning out of one environment, and how could we then find ways of fitting that usefully inter alia for prospective or predictive purposes in broadly similar environments. And one part of that is an epistemological dilemma, it seems to me. The other part of it is the inherent stochasticity in any of our modeling applications, which probably gets in the way. And those may pose real limits on what it's capable to do by cross-learning. Do you want to react and maybe ask?
Well, this is really a short comment that, of course, this consideration of generating a model and avoiding the problem of overfitting is at the very heart of learning theory, for obvious reasons. And one of the ways that people realize that you have a kind of a safeguard, or at least you diminish the danger of the overfitting, is that you actually penalize the usage of more and more parameters. So you assign a cost function to that, and then the kind of an Occam's razor kind of thing. So it forces you to optimize basically between the number of parameters and the fit.
Yeah, exactly. And I'm not at all claiming that people don't have a way of dealing with this, but I just maybe like to connect to Ross's talk yesterday, because one of the things about agent-based models in particular is they have absolutely loads of parameters. So this problem is really can be a big issue there. And Ross kind of, in some sense, was dodging a little bit the question. But one of the things he said is that really to use these kind of agent-based models well, you need a lot of expertise and training and this kind of this apprenticeship method of training people. And really the reason why it's not easy to use those models well is this. Because you really need to get a grip on this overfitting problem.
But what's interesting is that when you use those models, 70% of the time, and Ross was saying, when you use those models, even though they may overfit, 70% of the time, only 2 or 3 very simple rules emerge. So, you have complexity and simplicity coexisting. And I sometimes think maybe part of the problem we have is overfitting ourselves with complexities. We're always looking at complexity, when maybe what we should be looking for is the simplicity inherent within it. Otherwise we tend to overfit ourselves with complexity, so it's just a sort of reflection. I know I'm the moderator and I shouldn't really be doing this. Okay, any other questions? I'll hand the mic over. Any other questions?
Well, maybe let me just respond to this point in particular, and just make reference to rather old knowledge from the statistics literature. So there's this famous Box-Jenkins approach for time series modeling, which I guess, was before my time, but I guess it was kind of surprising at some point where people learned that actually simple auto-regressive models with small numbers of parameters can actually be more predictive in places of some time series than kind of more physically based models, which include a lot of the complexity. You can really race these things, and you have enough data, you can say, as you run them along, which one is predicting better. And you find that the model, which is very simple, actually can sometimes be doing better than ones which in some sense are more mechanistic and include more knowledge. So that was an eye-opener, I think, for time series modeling community. And relates to this.
Lex? Final question before, well actually no, we've got 5 more minutes. So.
I would like to go back to the slide where you introduce Frank Knight, the distinction between risk and uncertainty.
Oh, that was really interesting.
My question is, could you elaborate a little bit on under what conditions you think, or following Frank Knight, you would think that, let's say, this stochastic modeling, this stochastic method, with all of the caveats that you mentioned, is applicable at all?
So I can see why you asked this question in the light of the talk which you gave yesterday, because you were basically saying that the future is generated by the actions of people actually living in the system, whatever. And so one of the things about risk versus uncertainty in the perspective that Knight had, and I'm not really an economist, I don't know this too well, but how I understand it is that essentially the risk, to use this kind of approach, you need to write down some probability distribution for the possible outcomes that you expect the system to be capable of generating. And okay, maybe it's not a good model, you may need to refine that model as you get more observations and so on. So it's not quite the case that you need to enumerate all outcomes. You can write down a probability distribution which has some parameters, and you can update those parameters in the light of new information as you go along. But you do still, but that is still a restriction of some form of possible outcomes, because you need to at least write down a class of functions that can be parameterized in some way. And if the true future is not a member of that class of functions, you can write down sine function with some variable frequency, and no choice of that frequency will make it well approximate an exponential, for example. So the future just may not be in the class of models which you're considering, in which case you're sunk. But if you have a sufficiently general class of possible, if you allow for sufficiently general class of outcomes, you may hope that you can still capture what the actual future will be, but I doubt that it can ever be guaranteed. So somehow, I think your point absolutely stands in my mind in this setup too. But I don't think it's quite as black and white as saying that it's impossible to write down all possible futures. You can make a guess at the classes of futures and write down some set of functions that may capture those, and hope to adapt parameter values in the light of new information as time goes on. That's probably the best you can do. But it doesn't invalidate your assertion, I would say.
Any other questions at all? So it leaves me to thank you very much, Colm, for a very insightful and
thank you.
and also a reminder not to trust intuition always. And thank you very much indeed. Thank you.
Thank you.